knowing what those formulation considerations would be in response to how the drug might degrade.
Is that still further degradation?
So if it's an alkene, maybe, because alkenes are very susceptible, but if you just see one aromatic ring, usually you wouldn't say photodegradation. It usually has to be like multiple aromatic rings stuck together. But if you were in an exam to identify like something that has one double bond as photodegradation, it would be, I would say it's correct. I can't say it's not possible because it's possible. But generally, if you're really just looking for the degradation, you're looking for a lot of double bonds or a lot of ring systems. Usually if you just say see one or two, you would still have to test it for photodegradation, but it probably wouldn't matter too much. So next lecture was rates of degradation. So remember in that lecture we did a lot of looking at the different rate equations, right? And I'm not going to ask you about rate equations. We went through those so that we could really just get to this equation here, looking at how to estimate shelf life or T90 values. So for rates of degradation, you would just remember rates will increase when you increase temperature. So when you're looking at hydrolysis, oxidation, racemalization, photodegradation, they will all be higher, degrade faster when you increase the temperature. But remember, I also mentioned that when we're looking specifically at racemalization and photodegradation, those aren't necessarily linear related to temperature. Remember when we talked about looking at hydrolysis as a route of degradation, we could use the Q10 method to look at the shelf life at different temperatures, and that was because the relationship between degradation and temperature is linear for those types of degradation reactions, but it's not linear for racemalization and photodegradation. In other words, in an exam, I wouldn't give you something that's going to degrade by racemalization and ask you to calculate the degradation at different temperatures. Really only for hydrolysis we're using those Q10 methods. So we also talked about the order of reactions. So we had the main two orders of reactions for pharmaceutical products are pseudo first order and first order reactions. So that's mostly chemical degradation in solutions. And then we also had zero order reactions. So the zero order reactions are concentration independent, and that's mostly what's occurring when you have chemical degradation in a suspension. So first order, we're looking at concentration dependent degradation in the solution. Zero order are concentration independent in the suspension. So we can calculate the shelf life of chemical degradation reactions using this equation here. And then the shelf life, remember, it's the time that it takes a drug to degrade by 10%. So that's why it's called T90. It's the part where you have 90% of the drug remaining in the formulation. And then for these, you just have to be careful to use the right one, so the right order of the reaction. So if I give you something that's in a solution, you would be using the first order. And if I give you something that's in a suspension, you would be using the zero order. And one way to double check to make sure you're using the right one, if I give you a K value, and the units of the K value are just 1 over time, so 1 over minutes, 1 over days, 1 over hours, you would know that it's a first order K, first order rate constant. If I give you a rate constant that's some kind of concentration term over time, that's a zero order rate constant. And that would be something in suspensions. And then again, remember I'm giving you these equations for the exam, so you don't have to memorize them. I'll give you the units too. But just remember to pay attention to the units, and then you'll be fine choosing the right equation. So for the rates lecture, really the only equation then, we're really looking at the shelf life. And remember, for that equation, you really just need to get that K value, the rate constant. So one of the ways to get the rate constant are looking at these pH rate profiles. So in this example, we're looking at calculating the shelf life of a drug in an aqueous solution at a given pH based on this hydrolysis degradation curve. So I told you it's hydrolysis, I told you it's in a solution, so it's a first order reaction, right? So you would use the T90 equals 0.105 over K. So we need to get our K value from this graph. So we're looking at a pH of 4.5, which is around here. So our log of K is -7. So to get K, we have to take the anti-log of that, right? So the anti-log of -7 will give us our K value, which is just 1 times 10 to the -7. And the units you get from the graph are 1/minute. So you just plug that K value into this equation, and you get your shelf life. Yeah, so I said, yeah. Yeah, so there's several ways you can tell it's first order. So one, because I said it's a solution. And the other way is that the K value is in 1/time, 1/minutes. So those two are clues to the order of the reaction. So you know it's a first order reaction. The third way is that, remember, if you are calculating something in a suspension, I also have to give you the concentration of the drug and the drug solubility. I didn't give you that in this question. So all of those can lead you to assume that it's going to be a first order reaction. So if you go through all the math and plug your K value into the T90 equation, you'll get a shelf life of 2 years. And then remember, these are always related to the temperature, right? So this would give you the shelf life at a storage condition of 25 degrees Celsius, right? Because that's where you got your K value at that temperature. So you always have to match a shelf life with the temperature, with the storage temperature, because remember, when you change the temperature, it changes the degradation rate. So it'll be different at different temperatures.
Go over how you got log K equals -7.
So log K is -7 from this graph here. So because I gave this pH of 4.5, you want to look at a pH of 4.5 on this graph, and then you just get the -7 from the y-axis.
Right.
And then you have to take the anti-log to get your K value. And then always remember to check units. So when you plug this into the T90 equation, you're going to get the shelf life in minutes, and then you just would convert that to something reasonable, or to convert it to whatever, however I'm presenting it in the question, so you convert to years. 2 years would give you, so the T90 equals 0.105 over K. So our K is 0.105 over 1 times 10 to the -7. So T90, I write it down. Comes out to 105 minutes. So then you have to do times 1 hour over 60 minutes, times 1 day over 24 hours, times 1 year over 365 days. And that gives you 2 years. I'm going to send all this to you, so don't worry. Don't write it down. So the next question is then to go the next step and then estimate what the shelf life might be if you store this drug at 5 degrees Celsius instead of 25 degrees Celsius. So remember, to do that, we use the Q10 method. So we have our shelf life at 25 degrees Celsius, so that's our K1 value, right, would be 1 times 10 to the -7. And we also already know our shelf life at this, which we calculated as 2 years. So remember the Q10 method, you have the 2 times delta T over 10 will give you the shelf life of K1 over the shelf life of K2. And then your delta T is equal to the T1 minus T2. So just always remember to match everything up. So in this example, T2, we're solving for 5 degrees Celsius. T1 is what was given, would be 25 degrees Celsius. And then remember our T90 K1 is 2 years. So we get from that 5 minus 25 over 10 I'll give an example of how to do that on the equation sheet. For the exam, for the calculator, because that part, doing 2 to the minus 2 might be confusing on the calculator, but I'll put a stepwise way to get that number. So this will give you the, right, 2 years over the T90 K2. So then you're solving for the T90 K2, which will be 8 years. So that's this one. So then another thing that you can do with these shelf life equations is then also estimate the shelf life as if this was formulated as a suspension at a concentration of 0.8 molar, knowing the intrinsic solubility of the drug. So to do that, you're going to have to convert between the two different rate constants. So remember the rate constant of our first order was 1 times 10 to the minus 7, right, minutes over 1. And then remember this equation that has the rate constant at 0 order reactions, which is K0, is the rate constant from first order reactions times the solubility. So you would get your K0, 1 times 10 to the minus 8 mole over minute. Because remember, so now we multiply by 0.1 molar. Okay. And then you would plug this into the other T90 for 0 order reactions, which is 0.1 times A0 over K0. And that'll give you the shelf life for your 0 order reaction for this formulation. So if you plug those numbers in, you'll get 15 years. Yeah, so it was just this K value that we got. So the next lecture was focused on expiration and beyond use dates. So the big takeaways from this lecture are the difference between expiration and beyond use dates. Expiration dates are assigned by the manufacturer and are usually saying that the drug has to maintain 90% potency during its shelf life under specified storage conditions. So expiration dates set by the manufacturer. Beyond use dates are those that are assigned by compounding pharmacists. So if you're making compounding formulations, you would use a beyond use date. So beyond use dates, you're taking information available by the manufacturer into account for chemical degradation if it's available. Otherwise, you're assigning them based on USP recommendations. And then remember, these recommendations were different depending on the type of formulation. So anything that's non-aqueous, you would give it a beyond use date of 6 months. Something that's a water-containing oral formulation, you would give it 14 days at cold temperature storage. And then any topical formulations, you would give 30 days. And again, just remember that you also should take into account any of the manufacturer information. And this is mainly when you see a drug that might hydrolyze or oxidize.